Hi, I am Lopamudrashen. Welcome back to my channel Electronic Science Tutorial. I will start a new lecture series on NTA UGC NET and West Bengal SET exam for Electronic Science subject. Those who are not follow my channel, please follow my channel. If you like my channel, then please like, share and subscribe my channel. So let's start our class. In today's class, we discuss about the NTA UGC NET and West Bengal SET exam 2022. In this session, we cover in detail about this topic so that we can easily solve the previous year question paper of UGC NET Electronic Science. Each and every topic we can understand in easy and simple manner. So, let's begin our NTA UGC NET exam 2022 class. Okay. Today we talk about the electric field of PN junction diode. In previous slide, we will discuss about the PN junction diode under no bias condition, under forward bias condition and under reverse bias condition. Today we discuss about the next important topic of PN junction diode, that is the electric field calculation of PN junction diode. How this electric field we can define? So by this graphical presentation we can define the electric field. This is a PN junction diode. This side is P side, which is doped by group 3 element, and this side is N side, which is doped by group 5 element. So in the P side, the majority carriers are holes and the minority carriers are electrons, and in the N side the majority carriers are electrons and the minority carriers are holes. So here we write holes because this is P side, and here we write electrons because this is N side. This P side and this N side is the neutral region, and this junction region, which is called the space charge region or depletion region. We already talked about this topic. So what is electric field? Where the electric field occur? Electric field is created in the depletion region or in the space charge region because of the separation of positive and negative space charge densities. So what is the positive space charge densities and negative space charge densities? First of all, we show here the volume charge density distribution in the PN junction, where we can assume that a uniform doping, and we can assume an abrupt junction. Okay. So for the volume charge density distribution in the PN junction, we can assume first condition is uniform doping and the second assumption is abrupt junction. Right. So the electric field created in the depletion region by the separation of positive and negative space charge densities. So we can assume the space charge region abruptly end in the N region at x equal to plus xn, and in the P region its end in at x equal to minus xp. This is the positive charge density region and this is the negative charge density region. So how can we define? This side ends by x equal to positive xn, and this side is, this P side is ends at x equal to minus xp. xp is a positive quantity. Okay. So in this figure, in the below figure, in this figure, here we also write this side is x equal to positive xn, and this side is p side, that is x equal to minus xp, and xp is the positive quantity. So how can we calculate the electric field? From the one-dimensional Poisson's equation, we can calculate the electric field. So from the one-dimensional Poisson's equation, we can calculate the electric field, and it is defined by d square phi x divided by dx square equal to minus rho x epsilon s equal to minus dex by dx, and this is equation 1, where phi x is the electric potential and Ex is the electric field. This rho x is the volume charge density and epsilon s is the permittivity of the semiconductor. So this is the electric potential. This Ex is the electric field. This rho x is the volume charge density, and epsilon s is the permittivity of the semiconductor. So how can we define the charge density? The charge density are, first of all, rho x equal to minus ENA. Rho x equal to minus ENA. So this side is the positive charge density, and this is defined by minus ENA. Na is the, so this side is minus ENA. So the limitation is, no, the first of all the charge density we can define here, that is rho x equal to minus ENA. So this is the side. This side we can define by minus ENA. So Na is the charge density in the valence in the p side. Okay. So this is the minus ENA. E is the electronic charge. So what is the limitation, or what is the limitation? Minus xp to 0. So this is the negative charge densities. And next the positive charge densities, that means this side, that is defined by rho x, which is equal to END. ND means the charge density in the n side. So this is defined by a positive quantity. So here we write plus END. And this is the limitation. The lower limit is 0 and the upper limit is xn. So the positive charge density is assumed in this region 0 to xn, and the negative charge density, that is minus ENA, is assumed in this region 0 to minus xp. The positive charge density is END and the negative charge density is ENA. Positive charge density is defined by positive quantity and the negative charge density is defined by negative quantity. And so here we define minus ENA. So this is the charge density. Next, so from the so how can we define the electric field from equation 1? If we integrate the equation 1, the electric field in the P region is, if we integrate the equation 1, what we get, that is E equal to integration rho x by epsilon s dx, that is equal to minus ENA, because this is the P region and the P region density, charge density is minus ENA. So here we write, in the place of rho x, here we write minus ENA. So here we write ENA divided by epsilon s dx, that is equal to minus ENA epsilon s x plus C1, where C1 is the integration constant. Okay, so this is the electric field in the P region. So the electric field is assumed to be 0 in the neutral region. This is the neutral region. This is the neutral region, and this side is also the neutral region. The electric field is assumed to be 0 in the neutral P region. That means x less than minus xp. So in this region, the electric field is neutral region. So the electric field is assumed to be 0 because the currents are 0 in thermal equilibrium condition. As there are no surface charge densities within the p-n junction structure, the electric field is a continuous function and the constant of integration is determined if we setting that if E equal to 0 at x equal to minus xp. So the electric field in the P region is then given by E equal to minus ENA divided by epsilon s into x plus xp, and the limit is this. This is the equation 2. Right? In the same manner, if we consider the N region, how we can determine the electric field? That is, similarly for the N region, the electric field is E equal to integration rho x epsilon s dx equal to, the rho x value is, for the positive charge density, it is the value END. So here we write END divided by epsilon s dx, that is equal to END epsilon x epsilon s x plus C2, where again the C2 is the constant of integration or the integration constant. So if we said that E equal to 0 at x equal to xn, what is the, and electric field is continuous in the N region, so it is a continuous function. So how can we define this? The electric field in the N region is then defined by E equal to minus END divided by epsilon s into xn minus x, and this is the limitation. This is equation 3. So this is the electric field in the P region, and this is the equation of electric field in the N region. Okay. So the maximum electric field where occur? The maximum electric field will be occur at x equal to 0 condition. So from the previous equation, if we putting the value x equal to 0, we get the equation 2 and equation 3. If we putting the x equal to 0 value, we get the electric field maximum, that is E max, and that is equal to minus ENA divided by epsilon s dot xp, and that is equal to minus END epsilon s dot xn. From this equation, what we get? That is NAXP equal to NDXN. So this statement or this equation states the number of negative charges per unit area in the P region is equal to the number of positive charges per unit area in the N region. And from this graph, and it is a plot of electric field in the depletion region, and the electric field direction is from the N region to the P region or in the negative x direction. For the uniformity doped of p-n junction, the electric field is a linear function of distance through the junction, and the maximum electric field occurs at the metallurgical junction. That means an electric field exists in the depletion region when no voltage is applied between the P and N region. So this is the statement. This states that the negative charge per unit area in the P region is equal to the positive charge per unit area in the N region. So this is the electric field concept of PN junction diode. Okay. I hope you understand this topic. Thank you. With this, we have come to the end of our session. I hope you liked this video. Thank you friends. If you like my video, then please do like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.